today is the new day, but also it is the new topic. So we just want to start with the new topic, and this topic is called forces in equilibrium. Now, today is the new topic. We just want to talk about the new topic, which is called forces in equilibrium. So before we discuss the topic in general, we have to know the terminology. Now, we have said we just want to learn about the new topic called forces in equilibrium. So before we go ahead, by knowing the detail about the forces in equilibrium, how do we apply in our general life? But we have to know the terminology. The terminologies that have been applied in this topic. We just have equilibrium and we just have forces. The word force is not a new concept to us because we learned the word force when we were in Form 1. But the word equilibrium is just like a new word to us because we have not ever seen the word equilibrium in science. Now let us see what is equilibrium and what is the forces in equilibrium. And therefore, the force, according to the physics, the concept of the physics, we say force is the pull or push, is the pull or push experienced by an object, whether is at rest or is in motion. So the pull or push experienced by the body, that is called force. But equilibrium is the state of balance of an object. The state of balance of an object, when the body says to be in equilibrium, that is, it is at balance, it is balanced. So it is balanced because we say it is in equilibrium. So in other words, we say equilibrium is the state of balance of our body. Now, when we talk about forces in equilibrium, we are talking about the application of the forces and in which way this force will cause what we call equilibrium. And that's when we talk about forces in equilibrium. Now, let us see the more detail about it. Now, as we have said, we just want to talk about the new topic called forces in equilibrium. So the forces in equilibrium is the new topic, but we have to know the terminology that I've used to make the topic, the name of the topic. Now, the title of the topic is forces in equilibrium. Now, we have to know what is equilibrium and what is the force. The word force is not a new word to us because we learned about the force when we were in Form 1. Now we are discussing about the force and equilibrium. Equilibrium is the state of balance of a body. When the body says to be balanced, that is, we say it is in a state of balance, and we say it is in a state of equilibrium. And the force itself, it's the push or pull experienced by the body, whether in motion or at rest. So if that had been the case, we have known now what is equilibrium and what is the force. Now, equilibrium ni ile hali ya kitu kubalance, kujikuta katika hali ya kubalance. Now, and the force is that what we call a pull or push experienced by the body, whether in motion or at rest. Now, after we have seen what is the force and what is equilibrium, now we're talking about the force and how can you apply this force to make the body balance. How can you apply this force to make the body balance? Now we just have effect of turning forces. In other words, we just call it the turning effect of the force. And now the turning effect of the force is explained in such a way like this. Now let us see how to use this turning effect of the force. Now this is a band. This is a bench now. Therefore, let me apply two different forces. When you apply the force, now somewhere like here, I've applied this somewhere. Now, when you see this one, it will be moving like this one. I've applied. Now I'm rotating. But when I apply somewhere like this, now this one. When you apply the force to this object and you make it turn or rotate, we say the force applied on the body and causes the body to rotate or turn. That is called the turning force. So the turning force is the force that I will apply to this body and make it rotate. When I make it rotate, means that I'm turning the body. Now the force that is applied is called the turning force. So the turning force sometimes can rotate this object, but it can make this object rotate, but it will rotate in different way. But it will have the fixed point. it will have the fixed point. The fixed point is the place at which the body is free to move, but it is fixed, and it is called pivot. And now, when the object turns about the fixed position, the term results is known as turning effect of a force. So when the body is allowed to turn about the fixed position, the term that is no longer called the turning force, but it is called effect, the turning effect of the force. Now the turning effect of the force is resulted from when you have applied the turning force to the body, and you have made that body to rotate or to turn, but it is rotating about the fixed point, that is called the turning effect of the force. Now, why is it called turning effect of the force? Because the turning effect allows object to rotate about the turning point called pivot. The turning point is called pivot. Or the pivot, in other words, we just call it fulcrum. And therefore, we talk about the moment of the force. Now, the turning effect of the force is called the moment of the force. Now, let us see how we do this one. Now, we just want to know the turning force. Now, this is the rod. If this is the rod now, this is the rod. And the center of the rod, it is here. We just call it center of gravity or center of mass. The center of gravity or center of mass, it is a point at which the mass of the body says to be concentrated. That is what we call a center of gravity or center of mass. We'll discuss it later about it, center of gravity and center of mass. But I just want to show you, if this is the center of mass and it is concentrated at the center of if this is the uniform, this is the uniform body or uniform rod, mean that there is no variation in its length, there is no variation in its mass at every point that you touch. Now, when you look at here, you will definitely find that this center of mass, when you apply the force here, you will cause this object to turn and it rotates. So it will be rotating like this one. So it will be rotating going this way. But also when you apply this force somewhere here, you will cause this body to rotate. Now this will rotate in this way. Now the turning force, the force that will be applied to this load and will make this body to rotate or to turn. That is called turning force. But the force that will be applied to this object at its center, it will not cause this object to rotate, but it will move in a straight line. So that's how we'll talk about it. We talk about the line of action. So we just have the line of action and we discuss more about it. But what I wanted to show you is the turning force. Now, the turning force, the force applied on the body and causes that body to rotate or to turn, and it is called turning force. But when the body, now this is the body or the object, when it turns about the fixed point, when the object turns about the fixed point, the term results is known as turning effect of the force. Now, turning effect of the force is caused by the turning force. And why is it called turning effect of the force? Because the object is rotating about the fixed position. And that's why it is called the turning effect of the body. Now, the turning effect of the force, the turning effect of the force is what we call moment of the force. Moment of the force. Moment of a force. Now, the moment of a force, we're talking about turning effect of the force. Now, if moment of the force is called turning effect of the force, how do we apply this one? Now, moment of the force is obtained by following, is determined or depends on the following factors. Now let us see. Therefore we say the force applied on the body and causes that body to rotate or turn is termed as turning force. Kwa turning force ni nguvu inayosababisha kitu kizunguke. Kani ambayo inasababisha kitu kizunguke tunaita turning force. Na endapo hiki kitu kitazunguka katika mahala fulani kimeshikiliwa, hiyo tunaita turning effect of the force. And therefore that's why we say when the object turns about a fixed position, the term results is known as turning effect of the force. Now, turning effect of the force is the result of the turning force. And turning force is the force that when applied to the object causes it to rotate or to turn. Kani ambayo inasababisha kitu kizunguke inaitwa turning force. Na endapo kitu kinazunguka kiwa mahala fulani kimeshikiliwa kinaitwa turning effect. The turning effect of the force is what we call moment of the force. Now, this is what we term as moment of the force. Why is it called moment of the force? This is because the turning effect allows an object to rotate about a turning point or pivot. So this is what we talk about, turning effect of a force and moment of a force. Now, let us see the other thing that we discuss about forces in equilibrium. So now we have seen what is turning effect and we have seen what is moment. Now let us discuss more about moment of a force. As so long we have seen moment of the force is the turning effect of the force. Now let us see more detail about moment of a force. Now we have said turning effects. We have seen turning effects that is called moment of a force. Now the moment that there are some factors that affect the moment of the force and which is called turning effects. Now the moment of a force that is turning effect depends on the size of the force and the perpendicular distance from the pivots. Now, the factor that affect the moment of the force, we just have size of the force and the perpendicular distance from the pivot. So let us see these factors affect. Let us see these factors, how do they affect. Now, and therefore we're talking about moment of a force. Now we have said the moment of a force is the turning effect of the force. Now, if that is the turning effect of the force, but it depends on the size or magnitude of the force applied. Magnitude of the force, of a force, that is force. And also depends on the second issue, depends on the perpendicular distance. Perpendicular distance from the pivot. Why do we say perpendicular distance? Now, when you have drawn this one, this is something that we draw. And we have said, this is the rod. When you just want to balance it, like this one, you will allow this body to rotate, this rod to rotate in such a way that it will be balanced. Now, when you just want to balance this one, you will talk about this is pivot. As we have said, when you talk about moment of a force, you're talking about turning effect. And we have said the turning effect is caused by the turning force, which causes the body to rotate or turn about the fixed position. Now, this is the fixed position, which is called pivot, we have said. If this is pivot, now we have said this is pivot. Now, we have applied a force somewhere here, and we have applied the force somewhere here. Now, this force, this is force 1, and this is second force. Now, you have balanced this load. Now, if you have balanced this load, you have the distance from the pivot to where the force is applied. Now, that is what we call perpendicular distance. Why is it perpendicular? It is simply because this force is pushing downward, and the distance is coming from here and they perpendicular to each other. That means that when they meet together, they form 90 degrees. That's why we say perpendicular distance from the pivot, because the force and the distance are perpendicular to each other. That's they form 90 degrees, and that's why we say perpendicular distance. And now the moment of the force depends on the perpendicular distance, meaning that depends how far are you from the pivot. Example, the moment of the force at point A. Now let's say you just have this one. You just have, this is the load. This is the rod. Now if this is the load, let's say this is pivot. Now at this point we just have point A, and then we have this point B, and then we just have here point C. Now point C. Now let's say you have applied here force 1, and here you have applied force 2, and here you have applied force 3. That is to say, the force that you have applied here are equal in magnitude. Let us assume the force 1 is equal to the force 2 and is equal to force 3. Now, if that had been the case, you have the same magnitude of the force, but you have different position from the pivot. Now, from here up to point A is very near from the pivot, and point B is far away compared to point A from the pivot. and point C is farthest from the pivot compared to the other point A and B. Now, which one have that greater moment of the force? The point A have small magnitude, moment of the force. The moment of the force of point A is smaller than point B, and this is smaller than point A. And then we say the moment of the force at point C is greater. It is greater compared to the moment of the force at point B, and the moment of the force at point B is greater than compared to the moment of the force at point A. Why is it possible? Why is it possible? It is simply because the distance from the pivot at point A is smaller than the distance from the pivot up to point B. And then the distance from the pivot to the point B is smaller than the distance from pivot to the point C. And that's why the moment of the force increases as you increase the perpendicular distance. But also, when you assume that this is point A, and this is point A, at point A, this is, let's say this is 5 centimeters. From the pivot up to the point A is 5 centimeters. Now, you just want to say that F1 is valid. Now, I've put 5 Newton. Then I move, I put 10 Newton. Then I move and put 5 Newton. So there is a variation Newton. We say that moment of the force increases as we increase the magnitude of the force. That's why the force with 5 Newton at the same distance cannot be compared to the force of 10 Newton. The moment of the force with 10 Newton at the same point. That is to say, the moment of the force is equal to force times distance. And that's why I say moment of the force increases as you increase the force of an object, and also increases as you increase the distance of an object from the pivot, the distance of the force from the pivot. The distance of the mass from the pivot. Now, this is how we say moment of the force depends on the size of the magnitude, and also the moment of the force depends on the perpendicular distance from the pivot. Why do we say perpendicular distance? Because the force and the distance are perpendicular to each other. That's why we say perpendicular distance. Now, let us see the other things. And therefore we say factors affecting moment of the force, that is turning effect of the force, depends on. The first factor is the size of the force. The second factor is the perpendicular distance from the pivot. Now we have two factors that are affecting the moment of the force. Now we have the size, which is, in other words, we say the magnitude of the force applied, and then the perpendicular distance from the pivot. That is all about the factors affecting moment of a force. Now, as we have seen, the moment of the force is the product of the moment of the force is the product of the force and the distance, perpendicular distance. Now let us see the other things. Now, let us see clockwise and anti-clockwise rotation. As we have seen, we have said that the turning effect of the force causes rotational motion. Kumbe turning effect inasababisha rotational motion. Then, a body is considered to rotate in the positive direction if it rotates in anti-clockwise direction. It is said to be, the body is considered to rotate in a positive direction if it rotates in anti-clockwise direction. And a body is considered or said to rotate in negative direction if it rotates in clockwise direction. That is to say, the clockwise rotation of an object is always taken to be negative moment, while the anti-clockwise rotation or turn is taken as positive moment. That is, we say, consider and start. You see, now this is body A and this is body B. Now, this, as you have seen, this is an alloy. Huu ni mshale, na huu hapa ni mishale miwili yote. Now, this is an alloy and this is an alloy. Now, if this is an R and this is an R, we say A, B are different bodies. Now, A is called clockwise rotation, and this is B is called anti-clockwise rotation. That is to say, when the body rotates in this way, that is in this direction, we say the body says to be in the clockwise rotation. To be offered the clockwise rotation, that is called negative rotation. So this is called negative rotation. But when the body is said to be rotating in this way, we say the body says to rotate in anti-clockwise rotation. So the body is considered to rotate in a positive direction. So going this way is negative direction, and going this way is called positive direction, and it is called anti-clockwise rotation. And this way is called clockwise rotation. So this is what we talk about, clockwise rotation and anti-clockwise rotation. So going this way, anti-clockwise rotation. But going this way is clockwise rotation. And they are shown here by negative sign and positive sign. Now let us see more detail about clockwise moment and anti-clockwise moment. Now, anti-clockwise moment we have seen the clockwise direction and we have seen the anti-clockwise direction. We have said a body is considered to rotate in the positive direction if it rotates in anti-clockwise direction. And we have said this is what we term as anti-clockwise direction. Now this is anti-clockwise direction. And this going this way, that is clockwise direction, and it is termed as negative direction. So this is negative direction, but this is the positive direction, and it is called anti-clockwise direction. And now, when you just use the rod, this is the rod. Now this rod, when you see that you have applied maybe here, this is F. Let's say this is mass 1, and this is mass 2 here. This is mass 2. Let's say here, you have applied here, it is mass 3. Then we have this one. Now, the moment that will cause this load to rotate in this way, we just call them clockwise moment. That are called the clockwise moment. So if they are termed as clockwise moment, we say the clockwise moment at the moment of the force that will cause the body to rotate in the clockwise direction. We have said the clockwise moment at the clockwise moment of the force, at the moments of the force that will cause the body to rotate in the clockwise direction. When the moment that you have applied will cause the body to rotate in this way, you have applied what we term as clockwise moment. But when you apply the force and the moment of the force and cause the object to rotate in this way, mean that you have caused this way, you have caused this body to rotate in anti-clockwise rotation. And then we say this is called anti-clockwise moment. Now, the anti-clockwise moment at the moment that will cause the object to rotate in the anti-clockwise direction. So this is anti-clockwise direction. And that's why when you look at the diagram, I've written this is pivot. This now is pivot. Kama hii hapa ni pivot, umesababisha hiki hapa kitu kinazunguka kwenda upande huu, kwenda hivi. Hizo zinaitwa moment ambazo zinatokana hapa, zinaitwa clockwise moment. Na moment ambazo zinasababisha hiki kitu kizunguke katika mfumo huu, kinaitwa ni anti-clockwise moment. And all in all we consider about the pivot. Zote tunafikiri kuhusiana na pivot. And therefore we say the clockwise moment at the moment that will cause the body to turn or to rotate in the clockwise direction, that is negative direction. But when you apply the moment of the force and cause the body to rotate in a clockwise direction or anti-clockwise direction, we just give the difference between clockwise moment and anti-clockwise moment. And therefore, when you just want to talk about clockwise moment, you see here, we just have, this is what? This is mass 1, but how far is it from the pivot? That's what we say. The distance of the objects, the distance of the mass is always placed in, or it is varied, or it is assumed from, or it is measured from the pivot to the point where the mass is placed. Now we say, the distance that we're talking about here is the only distance that is measured from the pivot up to the point where the mass is said to be placed. Now, the distance of mass 1, it is from here up to where the mass is placed. Now, let's say this is x. And the distance, the perpendicular distance from the pivot up to M1, up to the second mass, is the distance from here up to, let's say it is distance y. And now, when you just want to know the distance that we might use when measuring the moment of the force, due to this mass, it is the only distance we measure from the pivot, that is fulcrum. Now the distance, the only distance from here up to the place the mass is placed, I mean up to the place, let's say this is Z. Kwa hiyo kumbe, umbali ambao tunazungumza nao hapa ni umbali tu wa kutoka pale pivot ilipo mpaka pale mzigo ulipowekwa, na sio distance ya kutoka from anywhere. The only distance that we deal with is the only distance from the pivot to the place where the mass is placed. And therefore we say the distance from pivot up to mass 1 is x, and the distance from the pivot up to mass 2 is called y. And the distance also from the pivot up to mass 3 is called z. So these are the only distances that we use when calculating the moment of the force, calculating the force required, calculating the distance from the pivot. This is what I'm talking about, the anticlockwise moment, anticlockwise moment, and clockwise moment. Now, let us see the other things called line of actions. Now, after we have seen what is moment of a force, we have seen clockwise and anticlockwise moments. Now let us see the very crucial and important thing in forces in equilibrium called line of action. Now the line of action is the line drawing from the point where a force is applied and through the body on which the force is acting. That is the line drawing from the point of action of the force through the body in which the body, which the force is acting. Example, you just have this an object. This is an object, or this is too bad now. Now, let's say this is an object. This is an object. Now, the line of action, now you have applied the force somewhere here. You have applied the force somewhere like here. If you have applied that force, now you have made this object to turn, where is that to turn? Or to rotate, or to move in a straight line. You have caused rotation motion or translation motion. But the line drawn from the point of application of the force through an object, through the body, that is called line of an action. So this is what we call line of an action. Line of action. So the line of action is the line drawn from the point of application of the force. So the line drawn from the point of application of the force through the body in which the force is acting. So we say the line of action of the force is the line drawn from the point where the force is applied and through the body on which the force is acting. Kwa kumbe line of action ni ule mchoro, ni mstari ambao unachorwa kuanzia pale ambapo ile point ambapo umeweka nguvu, umesukuma kitu, halafu kachorwa mstari kupitia kwenye kile kitu ambacho force inafanya kazi, ndio tunaita line of action. Kwa line of action tumechora hapa kwa sababu here we have applied the force. And now if here we have applied the force, now we have drawn the line from the point of application of the force through the body in which the force is acting. Now we say line of action. And that's why we say line of action is simply like this. Therefore, line of action is, and therefore we say line of action. Definition of line of action, we say the line of action of a force is the line drawn from the point where a force is applied. The point where the force is applied is here. And through the body on which the force is acting. Through the body. Now, this line drawn from the point of application is called line of action. Kwa force tumeapply hapa, lakini tunachora mstari kuanzia pale ambapo tumeweka apply kwa kunyosha kupita kwenye kile kitu ambacho force inafanya kazi. Now we say that is line of action. Now the line of action ni mstari unaochora kuanzia pale ulipoweka force, hapo ulipoapply force kupita kwenye kile kitu ambacho force inafanya kazi. Now that's how we say it is the line drawn from the point of application of the force through the body on which the force is acting. So this is called line of action. Now, how do this line of action affect the motion? How do this line of action affect the motion? Now let us see. Now, let us see the application of line of action. How does it affect the motion of an object? We say, we have seen this is the line of action. As we have seen, this is the line of action. If this is the line of action, now we just want to show how this will affect the motion of an object. When the line, we say, if this is an object, and the center of mass is here, center of gravity is here. Now we say, when the line of action passes through the center of gravity, the translation motion occurs. The translation motion occurs. Now the translation motion occurs when the line of action passes through the center of gravity. Now this is the center of gravity. Now if the line of action passes here, that is somewhere like here, this will undergo translation motion. Will undergo translation motion. The translation motion is the motion in a straight line. That's how we say the translation motion. But if the line of action does not pass through the center of gravity, the rotational motion occurs. When the line of action does not pass through the center of gravity, the rotational motion applied. Example somewhere here. When you apply the force here and you draw the line of action somewhere here allowance, mean that you have applied the force and you have caused the line of action to appear not in the center of gravity. Now we cause this body to rotate, and when the body rotates, it causes the rotation motions. Now the rotation motion occurs when the line of action does not pass through the center of gravity. But when it happens that, it can happen. When it happens that, the line of action, some of the forces passing through the objective's center of gravity and others will not pass it, will undergo combination of translation motion and rotation motion. Kwa hiyo inapotokea kwamba line of action, example, this is an object. This is an object. And we have seen the center of gravity. Imagine this is an object. We have seen the center of gravity somewhere like here. This is the center of gravity. Now, if you apply the force and you draw the line of action, you find that the line of action passes through the center of gravity. This object will undergo translation motion. Kwa kumbe line of action ikipita kwenye center of gravity, hiki kitu kinanyoka, kinatembea katika mstari ulionyooka, wala hakipindi wala hakizunguki. Lakini if it happens that the line of action does not pass through the center of gravity, this body will rotate and undergo translation motion. Example like somewhere like here. Kwa ukisukuma hiki kitu kitapinduka, kitaenda kinaviringika. Kwa hiyo ndio tunaita rotation motion. Kwa kitaenda kinaviringika. Kwa kitu kinapoenda kinaviringika, kina undergo rotation motion. But ikitokea bahati nzuri, baadhi ya forces zimepita kwenye center of gravity, zingine hazijapita. Maana yake ni kwamba motion itakayotokea ni kwamba hivi kitu kinaenda translation motion sambamba na rotation motion. Mfano, unaweza ukasukuma kitu katikati, ukisukuma kitu katikati kinakuwa kina rotate lakini in a straight line. Lakini kuna kingine ukikisukuma hakiendi, kinakuwa kinazunguka tu in the fixed position. Kwa maana unasukuma kitu cha mviringo, imagine kitu ambacho kinakuwa in cylinder form. Ukikisukuma katika center of gravity kinaenda straight huku kikizunguka. Lakini ukisukuma pembeni kinakuwa kina rotate, hiyo ndio inaitwa rotation motion. Lakini kuna mahali unaweza ukisukuma kinasukuma huku kina move at the distance, lakini vile vile kina rotate. We just call it a combination of translational and rotational motion. This is therefore we say, when the line of action passes through the center of gravity, the translational motion occurs. But if the line of action does not pass through the center of gravity, the rotational motion occurs. But if it happens that if the line of action of some forces pass through the object's center of gravity and others do not, the object will undergo a combination of translation motion and rotation motion. So that is all about the definition, the effect of line of action and how to differentiate within other things. Now let us see the other things as we have seen the introduction. Now let us see now the moment of a force in general, because we were discussing all about introduction. What is the moment of a force? Now let us see moment of a force. Now as we have said, we have seen the moment of the force, the turning effect of the force. Now, but we just want to know the real definition of the moment of the force. Now the moment of a force about the point is the product of the force, and perpendicular distance from the pivot. I mean the perpendicular distance of its line of action from the pivot. Now, including the line of action, including the perpendicular distance, including the force, that's how we obtain what we call moment of the force. Now, moment of the force is the product of the force and the perpendicular distance of its line of action from the pivot. Now, if that had been the case, mathematically we say moment of the force is equal to force times distance. And this distance we talk about here, the distance that we talk about here is perpendicular distance. That is to say, the distance is always perpendicular to the force. Now, they are perpendicular to each other. Now we say, moment of the force is obtained by taking force times distance. Now, force times distance. But remember, force is measured in terms of Newton, and distance is measured in terms of meter. And that's why we say, if moment of the force is equal to force times distance. Now force is measured in terms of Newton and distance is measured in terms of meter. Now we come to conclude to say the SI unit of moment of the force is Newton meter. Now when calculating moment of the force, you must find out the force in Newton and you must find out the distance in terms of meter. And this is where we say the SI unit of moment of a force, the SI unit is the Newton meter. So, and therefore, this is how we say about. Now that's therefore we say the moment is the product, is the moment of a force about a point is the product of the force and the perpendicular distance of its line of action from the point, from the pivot. It's written point, but it is called pivot. Now, mathematically, when we say about the product, that is to say the force multiplied by perpendicular distance. Now, force is measured in terms of Newton and distance is measured in terms of meter. Now we say moment of a force is equal to F times D. That is force times distance. And therefore we say the SI unit of moment of a force is Newton meter. Kwa maana ukichukua force ukazidisha na perpendicular distance unapata kitu ambacho inaitwa moment of the force. Now perpendicular distance from the pivot and it is measured in terms of Newton meter. Now that's how we talk about it. Now let us see an example about this one. Now, study example, a line of action of a force of 90 Newton acts at a perpendicular distance of 2.5 meter from a point. Find the moment of a force of that point. Now, the line of action of a force of 90 Newton acts at a perpendicular distance of 2.5 meter from a point. Now, find the moment of the force of that point. Now when you look at the question, you will definitely find that we've been given the force, which is 90 Newton, and we've been given perpendicular distance, which is 2.5. Now that are given. Force is equal to 90, force is represented by F, now is equal to 90 Newton. Perpendicular distance, which is B, is equal to 2.5 meter. Now the moment of a force is equal to what? Now formula, you have to write a formula that will be used to solve this problem. Now the moment of the force is equal to force times distance. Now if the moment of the force is equal to force times distance, now force is 90 Newton, and now distance is equal to 2.5 meter. Now 90 times 2.5 is equal to 225 Newton meter. Now the moment of the force is equal to 225 Newton meter. So we have obtained 225 Newton meter by multiplying this number, force and distance. So that's how we could have used to find out what is moment of a force. So moment of a force is equal to force times distance. And the force should be given in terms of Newton, and the distance should be given in terms of meter. And then we get Newton meter after we have multiplied. That's how we have got it. Now let us see the other things here. The center of mass. Now the center of mass, that is, we say, the center of mass of an object, it is the point at which the system of the particles forming up the object appear to be concentrated. Now, at the point at which the mass said to be concentrated, we say that is the center of mass. Now, let's look at the center of mass. When you talk about center of mass, what do you mean? I've said the center of mass, it is the point at which the mass is said to be concentrated. And definitely the center of mass is always at the center of the body. But if only the body is uniform. When you talk about uniform, you mean of the things that have got no variation in its mass at any point. Example, this is an example. I think it is uniform. So I'm not so sure because I've not measured it. So when you look at this one, if I want to determine where the center of this object, I must find at the center of the object, it is where the point balances. Kwa nikitaka nijue center of mass iko wapi, naangalia balance ya hiki kitu. Naangalia balance of the body, pale takapo balance. Now here, the body have balance. Now if it is a balance, it is here what we call the center of mass. Now the center of mass is here. Now if I just want to know the center of mass is here, when I take this one, this is my pivot. Now I put it somewhere like here. So it becomes inadondokea kule ambako kuna uzito. Na nikiweka huku inadondokea kule kuna uzito. Even I can even balance it like this one. So it falls where the mass is said to be concentrated. And that's why I've said the center of mass is the point at which the mass of the body is said to be concentrated. Pale ambapo uzito ulipo ndipo tunasema center of mass. Now center of mass for uniform object, for the uniform object, the center of mass says to be at its center, at the midpoint of the body. At the center of the body. Now this is the center of mass. That's why I can even balance whatever I do. But when I take it somewhere here, I cannot even balance. But I can allow it to rotate. Now the center of mass is just like here. For center of mass, the point at which the mass of the body is said to be concentrated. That's why we talk about the center of mass. Now let us discuss about the other things. Now in rotational we just say all the points in the body are said to rotate in a single line. And that single line is called axis of rotation. Kwa maana kitu kinapokuwa kina rotate somehow like this one, kina rotate, maana yake ni kwamba vitu vyote vinakuwa vina move in a single line. Kwa ile line, a single line ile tunaita axis of rotation. Kwa maana the body is free to rotate in the single line, and this is what we call axis of rotation. And that's why we say the center of mass is the point at which the system of the particles forming up the object appear to be concentrated. Or in other way, we can say is the point at where the mass of the body is said to be concentrated. That is what we term as center of mass. Now, the center of mass is when we time at the point at where the mass of the body is said to be concentrated. But you just not. In rotational motion, all points in the body move in a cycle around a single line called the axis of rotation. So they move in a cycle but along a single line. Kwa maana zinazunguka katika cycle rotation moja, lakini kuna sehemu ambayo inaitwa single line. Kwa hiyo katika sehemu moja zinazunguka katika sehemu moja, lakini zinazunguka katika mduara lakini kupita katika sehemu moja. That is called the axis of rotation. Sasa, now let us talk about the principle of moment. We have seen what is moment. Now, what is the principle of moments? Now, consider the diagram below, in which the body, that is rod AB, is free to rotate about point O. The body, that is the rod, is free to rotate about point O. So, the diagram below is the rod, and it is given as the name AB. But it is free to rotate about point O. Now, which, when you look, this is the body. Now, it is free to rotate at point O. Now, it have got this force and this force. Now, this is force 1 and this second force. This is distance 1 and this is the second distance. Now, this is called pivot or fulcrum in the other way. So, this is the rod, but it is free to rotate in the single line called axis of rotation, and in the other way we just call pivot. Now the two parallel forces acting on the rod AB. This is F1 and this is F2. Now they are called parallel forces. Now we say, if the rod shows no tendency of turning either clockwise or anti-clockwise about point O, then the positive and negative moments acting up on the rod must be equal in magnitude. If we have seen, when you go this rotation, that is clockwise rotation, and going this way, that is anti-clockwise rotation. So if the rod shows no tendency of turning either clockwise or anti-clockwise about point O, then the positive and negative. So this is positive and this is negative. So if there is no tendency of rotation motion or turning effects, the body says to be balanced. But it is balanced because the moment of the force, that is clockwise moment, and the anti-clockwise moments are equal in magnitude. That's why we say then the positive and negative moments acting upon the rod must be equal in magnitude. This is what called the principle of moment. And therefore, the principle of moment states that for a system to be in rotational balance, ili system hiyo katika rotational balance, the total clockwise moment must be equal to the total anti-clockwise moment. So the sum of anti-clockwise moment is it is from here up to here. All the force that act in this side, they will cause this body to rotate in anti-clockwise direction. And all the mass that will be placed from here up to here will cause this body to rotate in clockwise rotation. And then we say clockwise direction. And therefore we say the sum of the clockwise moments, the moment that will be obtained here, should be equal to the moment will be obtained here. And this is what we call the principle of moment. Now, the principle of moment states that for a system to be in rotational balance, the total clockwise moment must be equal to the total anti-clockwise moment. Kwa za huku, moment za huku tunaita anti-clockwise moment, na moment za huku tunaita clockwise moment. Jumla ya za huku zote, hata kama ziko 5, na jumla ya za huku zote, hata kama ziko 6, sawa sawa na za huku. Kwa hiyo za huku ni sawa na za huku, na hiyo ndio inaitwa principle of moment. Now, principle of moment, clockwise moment is equal to the anti-clockwise moment. Mathematically, we say the total clockwise moment should be equal to the total anti-clockwise moment. The total clockwise moment should be equal to the total anti-clockwise moment. That is F1, F2, F2 and D2 is equal to F1, D1. That is why, let us see here, it is here. We have said moment is equal to force times distance. Now, anti-clockwise moment is F1 times distance 1. And clockwise moment is d2 times f2. That's why f1 times d1 should be equal to the f2 times d2 to obey the principle of moment. Now that's how we say it is f2 d1, f2 d2 is equal to f1 d1. That's how we apply. If we use science, the clockwise moment plus anti-clockwise moment is equal to 0. How? Let us see this. Now, if this is what I've chosen, if this is what I've made, now I've said when you apply the force and you cause this body to move, to rotate in this way, this moment that you have applied to rotate this clockwise direction, we just call it clockwise moment. And this is anti-clockwise moment. So the force that will be applied here will cause anti-clockwise direction. And therefore, this we say anti-clockwise moment. Anti-clockwise moment is always positive. Now it is positive m. Should be equal to anti-clockwise moment. Now let's say it is negative m. Because the negative moment that is clockwise moment. And the positive moment that is called anti-clockwise moment. Now mathematically, if this is positive and this is negative, but they are equal in magnitude, but different direction. They are equal in magnitude. Clockwise moment and anti-clockwise moment, according to the principle of moment, they should be equal. That is, they are equal in magnitude, but different direction. And that's why when you see here, you will see that we have here positive m, and here we have negative m. Now, when you apply the principle of mathematics, this is m. Taking this to the other side becomes positive. And now here you leave 0. And that's why we say, mathematically, when you apply science, you will say clockwise moment. We say clockwise moment plus anti-clockwise moment is equal. Now, it is clockwise moment plus anti-clockwise moment should be equal to 0. Now, this is what I've said. Now, all the moments which are found in this side, this is the border, unimpaka. This is the border, unimpaka, ambao una differentiate between clockwise moment and anti-clockwise moment. Kwa hiyo nikiweka hapa force, nikaweka hapa force, alafu nikaweka force hii hapa, nyingine force hii hapa, nyingine hii hapa force. Force 1, force 2, force 3. Hizi hapa zote nikijumlisha lazima iwe sawa sawa na jumla ya hizo. Kwa moment nitakazozipata za huku sawa sawa na moment za huku. Hiyo ndio tunaita principle of moment. Na za huku tunaita clockwise anti-clockwise moment, na za huku tunaita clockwise moment. And that's why we say the principle of moment states that for the system to be in rotational balance, the sum of the anti-clockwise moment should be equal to the sum of clockwise moment. That's what we talk about. So we're talking about clockwise moment and anti-clockwise moment, but there should be the same in magnitude. There should be equal in magnitude, but different direction. That's what we talk about in moment, the principle of the moment of the force. And this principle of moment is what different we are going to apply when solving these questions. But the distance that I've said, the only distance that we deal about is the distance from the pivot to where to the place where the mass is said to be concentrated. That is the distance that we're going to talk about it. Now let us see some example to apply this principle of moment. And therefore, by conclusion, we say, if the system is in a condition of rotation balance, that is, the total clockwise moment and the total anti-clockwise moment are equal in magnitude, but different in direction. This is what is called the principle of moment. Now, the principle of moment is all about the total anti-clockwise moment should be equal to the total clockwise moment. And that's what we call the principle of moment. Now, some examples here. We just have the first example here. A uniform metal loop is pivoted at its center. A 20-gram mass is placed at the 10 centimeter mark, and a 50-gram mass of the 40 centimeter mark. At what mark must the second 50 gram mass be placed for the system to be in rotational balance. A uniform metal loop is pivoted at its center. A uniform metal loop is pivoted at its center. A 20-gram mass is placed at the 10 centimeter mark and 50-gram mass at the 40 centimeter mark. At what mark must a second 50-gram mass be placed for the system to be in rotational balance? The first thing is to understand the question. Now let us talk about this question. Now, the question is, we have read the question, but the first point of the question is to understand the question. So you have to understand the question. After you have understood the question, you need to know what are the data given. And when you have known the data given, you have to know what are the meaning of the data. What is the meaning of the data given? Now, how can you apply? And then you have known how to apply, but the first thing that you have to identify from the question is to know the problem of the question. We have to know the problem of the question. Now, after you have known the problem of the question, you have to come up with the solution to the problem. The solution to the problem means that you have to know the formula or the way on how you could use to solve that problem. And therefore, from here, we've been taught a uniform metal loop is pivoted at its center. That is the first statement. A uniform metal loop is pivoted at its center. That is the center of pivotation. I mean, at the point at which the metal loop is pivoted as it is center. Why is it uniform? Why do we say uniform? It is uniform because when you measure the mass at every point of the loop, you'll find is equal to the mass at other points. Kwa tunapoita kitu uniform, tuna maana ni kwamba si mahala fulani ni kinene, sehemu nyingine ni chembamba, sehemu kingine kirefu, sehemu kingine kinene, yani that is not uniform. That is called non-uniform objects. And therefore, when we say uniform loop, metal loop, that is, it is uniform in its dimension and in its mass at every point of the loop. Now, it is pivoted at its center. It is pivoted at its center. As we know, a metal loop have got 100 centimeters. Now, when we say here is 0, and here it is 100 centimeters. So if it is pivoted at its center, that is to say, it is the midpoint of 100 centimeters. Now, the midpoint of 100 centimeters is at 50 centimeters. Now, I've understood. Now, the first statement I've drawn. Now, it is pivoted at its midpoints. So, a uniform metal loop is pivoted at its center. Kwa hiyo kumbe pivoted at its center ni katikati ya metal loop, ambao metal loop ina 100 cm. Kwa hiyo kama ni katikati, it is 50 by 50. Now, the second statement is that a 20-gram mass is placed at 10 centimeter mark. It is placed at 10 centimeter mark. Or if it is placed at 10 centimeter marks, and we have said from here to here is 50. Now 10 centimeter mark, that is from 0 up to where the place where it's written as 10 centimeter. Now let us assume the mass, this is 20. Now it is 20 gram. It is placed 10 centimeter from the point, the initial point. Now, it is placed 10 centimeter mark. Now, 10 centimeter mark, it cannot happen to the other side because from here is more than 50. If from here it is more than 50, now it is not, you cannot find 10 centimeter at this side. So 10 centimeter is obtained at this side. Now, the second statement is, and 50 gram of mass at 40 centimeter mark. At 40 centimeter mark. So we're still in the limit of 50 centimeter from 0. So you cannot write here 40 centimeter. You say from here up to here it is 40 centimeters. So you write in this side. Now it is somewhere like here. This is 50 gram. It is 50 gram. But it is 40 centimeter from here up to where the body is placed. It is 40 centimeter. Now the question is, at what mark must the second 50 gram mass be placed for the system to be in operational balance? Now we need to know the second 50 gram will be placed at what mark. Now, in order for the body to be in operational balance, you cannot place the second 50 gram mass in the same direction. You place it in the next direction. Now we say it is always placed in the other. The second, it is 50 gram. This is what we're talking. So the distance that we distance, therefore it is simply like this now. Let us see the diagram. And therefore, this is the diagram representation. This is the diagram representation of the question. Now this is 20 gram, which is placed 10 centimeter from 0. Now this is 50 gram mass, which is placed 40 centimeter from 0. And then O is taken at the center of the metal loop. Now this is center of the metal loop. That is midpoint, that is 50 centimeter. And is chosen at the axis of rotation. Now, the second mass should be placed to the to the another direction. That is to say, in order for the body to balance, you should place this one. Now 50 gram mass is placed X centimeter from the pivot. So this X centimeter is from the pivot at where the mass is placed. This is X centimeter. So it is from here up to here, it is X centimeter. Not from here up to here. It is from pivot to where the mass is placed, which is X centimeter. So that is what we've been taught to us. Now, since the metal is pivoted at its center, its weight can be concentrated at its center, that at the axis of rotation. Hence, the weight of the metal loop does not produce the moment. Why does it not produce the moment? Because when it is placed at the center of the mass, now the center of, it is the center of the loop, that is the center of mass, it is the center of mass. Now we say the mass of an object, or the mass of the loop, is at 0 centimeter from the pivot. Now if it is 0 centimeter, that is moment is equal to 0, because moment is equal to force and distance. And now distance from the pivot is 0. Now we say moment of the force is 0. And that's why we say, since the metal is pivoted at its center, its weight can be considered concentrates at its center and at the axis of rotation. Hence, the weight of the metal loop does not produce a moment. Now, this is the diagram representation, and we have seen. Now, if that had been the case, now let us talk about the forces. Now, when we just want to know forces, we just find forces for 20 gram. Now, we cannot obtain the force without converting this one into kilogram. So, converting this one into kilogram, that means we know 1 kilogram, the relationship between gram and the kilogram. That is to say, 1 kilogram is equal to 1,000 gram. That is to say, it is, you convert this one into kilogram. So, we divide it by 1,000. So we get 0.02 kilogram. Now, if this is the case, now we can convert this one into Newton, because we know force is equal to mass times what? Times G. Now, mass is equal to 0.02 kilogram times, now it is G, which is constant 10 Newton over kilogram. Now, kilogram and kilogram cancel. Now, force is equal to 0.2 Newton. Now, we have obtained the force for 20 gram, and we can definitely find. So we have used this formula to find out the force for 20 kilogram, and for 20 gram, which is equal to F force is equal to mg. Now 0.02 times 10 Newton. Now the force for 20 gram is 0.2 Newton. The same thing that we can use to obtain the force for second mass and for third mass in the way that we can see. Now let us see the other force. Now, as we have said, therefore, which is simple. We can find out the force for each mass. Now 20 gram, we can convert this 20 gram into Newton. That is 20 divided by 1000, that is times 10 is equal to 0.2. That is, since we know force is equal to mg, now the mass is 0.02, now times g, which is 10, then that's g is equal to 10 Newton per kilogram, and that's why we say 50 gram is equal to 0.5 Newton, and for 20 gram is equal to 0.2 Newton. We have used this formula, force is equal to mass times g. Kwa kama tumetumia mass mara g, sasa mass tunaibadilisha kwenda kwenye kilogram ambao tunaonesha pale ubaoni vizuri, then this is how we can obtain it. And therefore we say the second mass must be placed to the right of the axis of rotation to bring the rotational balance. Kwa ile mass ya 50 gram nyingine lazima iweke upande wa kulia ili kutengeneza rotational balance. Otherwise you cannot find the rotational balance. And that is why we say the distance. Now the distance that we're dealing with, how far the mass is placed from the axis of rotation or pivot. I mean the axis of rotation or pivot or pivot is the only distance we're dealing with. So the distance that we're dealing with is the distance from the pivot. Example, we knew here, this is the diagram. Now 50 gram is 10 centimeter from the pivot, and this 20 gram is 40 centimeter from the pivot, and this 50 gram is x centimeter from the pivot. Now let us see how we obtain this. As we have said, the distance we use is the only distance that we obtain, that is how far the mass is placed from the axis of rotation, from the fulcrum or from the pivot. Example here, you just have 50 gram, and here you just have 20 gram. But this 20 gram is 10 centimeter from 0 points. And this 50 gram is 40 centimeter from 0 points. And not from the axis of rotation or point pivot. Now, if from here up to here is 10 centimeter. And from here up to here is 50 centimeter. Now, mathematically, from here up to here is 40 centimeter. Now the distance that will be used for 20 gram is 40 centimeter because it is the only distance that we deal with. The only distance that we deal with is the distance from the pivot at the place where the mass is placed. But for this 50 gram, we know from here up to here. From here up to here is 40 centimeter. Now we know from here up to here is 50 centimeter. Now, if from here up to here is 50 centimeter, and from here up to here is 40 centimeter. Now, what is the distance from here up to here? That is 50 minus 40. Now it is 10 centimeter. Now, this is from here. The distance that will be used to find out the moment of the body for 50, the moment of the body from the 50, for the 50 gram. So, and the distance that we talk about, the second 50 gram, is the distance from the pivot to where the mass of 50 gram is placed. Now this is x. And this is what we've been told to find out. And that's why it is same like this one. Now 50 gram is x centimeter from the pivot. And 50 gram, this 50 gram is 10 centimeter from the axis of rotation. And this 20 gram is 40 centimeter from the axis of rotation. It's now we can obtain, therefore, moments. Now, moment of the body, anti-clockwise moment. Now, anti-clockwise moment, we just have the anti-clockwise moment, we just have this one. So, this is 50 gram, and this is 20 gram, and this is another 50 gram. So, this 50 gram is in anti-clockwise, clockwise direction. So, this is causing clockwise direction. And this 20 and 50 is causing anti-clockwise motion, clockwise direction. That is where we say anti-clockwise moment. The mass of 20 gram, that is 0.2 Newton, is 40 centimeter from the axis of rotation. Now, moment of the force is equal to 0.2 Newton times 0.4 meter. That is to say, we have converted this centimeter into meter for the principle that For the principle that moment of a force is measured in terms of Newton meter, and that's why we have converted this centimeter into meter, and that's why we say moment of the force for 20 gram is equal to 0.2 Newton times 0.4 meter. Now is equal to 0.08 Newton meter. But also in the same way we have another anticlockwise moment which is caused by 50 gram, which is equal to 0.5 Newton, is 10 centimeter from the axis of rotation. And that's why we say 0.5 Newton times 0.01, it is 0.01, which is equal to 0.05 Newton meter. So all these are called anticlockwise moment because they are in the same direction, they are causing the body to rotate in the same direction. And therefore the total anticlockwise moment is taken as this one plus this one. Now the sum of anticlockwise moment is equal to this moment and this moment, we get 0.13. How it seems like. Now let us see. Now this is the only diagram we have obtained. That is, this 20 gram we have converted into Newton and we have obtained 0.2 Newton. And this 50 gram we have converted into Newton and we have obtained 0.5 Newton. And then this 50 gram we have also converted into force, which is 0.5 Newton. Now we want to know the distance. We have known now the distance from the axis of rotation for 0.5 Newton, which is 0.1 meter. And also we have known the distance from the axis of rotation to the point at which the mass of 20 grams is placed, which is equal to 0.4. Now the principle, the clockwise moment. This is anti-clockwise moment. And clockwise moment will complies all these forces. Will complies two forces because they are in the same direction and they are placed in the same direction to cause this body to rotate in the same direction. And that's why we say for 0.2 Newton, that is moment of the force, that is moment 1 is equal to 0.2 times distance, which is equal to 0.4. Now, which is equal to 0.08. This is Newton meter. And now for this one, for 0.5 Newton, now is equal to moments is equal to 0.5 Newton times the distance, which is equal to 0.1 meter. Now is equal to 0.05 Newton meter. Now the sum of anticlockwise moment, is equal to this one plus this one. Now the sum of the anticlockwise moment is equal to 0.08 plus 0.05, which is equal to 0.13 Newton meter. So this is the sum for the clockwise moment. For the anticlockwise moment, if this is the sum of the anticlockwise moment, now we can find the sum of the other sides, the sum of the moment of the other sides. Now we just have only one force here. Here we just have only one force, which is equal to 0.5 Newton. If that had been the case, now the clockwise moment now is clockwise moment. The clockwise moment now is equal to 0.5 Newton times the distance now is x, which is equal to 0.5x. Now this is what? Now from the principle of moment we have said, that the sum of the clockwise moment should be equal to the sum of anticlockwise moment. And that's why we say now 0.13 is equal to 0.5x. Now you divide by 0.5, you divide by 0.5. Now x is equal to 0.26 meter. So we have obtained the distance from here up to here is 0.26 meter. And we have obtained this one after comparing the sum of the anticlockwise moment and the sum of the clockwise moment. Kwa hiyo kumbe za huku ni sawa na za huku. Hata kama hizi siku itakuwa 20, lazima ziwe sawa na ya huku hata kama itakuwa ni moja. Kwa sababu wote wako katika state of balance. Kwa sababu balance ya kitu, kama ninyi mnakuwa wengi zaidi, inabidi msogeze distance ili muweze kubalance na huyo hapa. No matter how the situation is, but what I'm talking is the distance from the pivot to the place the mass is placed in, and also the distance from the palm, and the magnitude of the force which is applied. Now, this is how we obtain. Now we have obtained here, it is 0.26 meter from the axis of rotation. Now this is how it seems to be like here. That is why we say the moment for the anticlockwise moment, we have 0.2 Newton times 0.4. That is 0.08 Newton meter. And for the mass of 50 gram, that is 0.5 Newton, is 10 centimeter from the axis of rotation. Now 0.5 times 10, 0.1 time is equal to 0.05 Newton meter. Now the total anticlockwise moment is equal to 0.08 plus 0.05, which is equal to 0.13 Newton meter. And for the clockwise moment, let x be the distance from the axis of rotation of 50 gram. This is what we have seen here. We have said the other 50 gram centimeter, 50 gram mass is placed x centimeter from the axis of rotation. Now the distance from the axis of rotation to the mass of 50 gram is x centimeter. And that is why we say let x be the distance from the axis of rotation of 50 gram. Now when you convert this 50 gram into Newton, you get 0.5 Newton. Now moment of the force is equal to 0.5 Newton times x meter, which is equal to 0.5 x Newton meter. Now the total clockwise moment is equal to 0.5 x. Now if this is 0.5 x, from the principle of moment, we say the total clockwise moment should be equal to the total anticlockwise moment. Now 0.5 x is equal to 0.13. Now, if that had been the case, now we divide it by 0.5, 0.5. We divide it by 0.5. Now, if that had been the case, when we divide by 0.5, 0.5, we obtain 0.26. But this 0.26 meter, we convert it into 26 centimeter. And therefore, the second mass, the second 50 mass, must be placed 26 centimeter to the right of the axis of rotation. That is at the 76 centimeter mark. Why is it 76? It is right here. We have just seen it here. If from here up to here is 50 centimeter. And then we have get x is equal to 26 centimeter. Now we take this 50 centimeter plus 26 centimeter. Now it is where we get 76 centimeter. Now we have obtained this 76 centimeter after taking 50 plus 26. So this is how we could have used the principle of moment to solve this problem. So let us see the other example. Now after we have seen the first example, now let us talk about the second example, which said that a uniform load with a mass of 120 gram and a length of 130 centimeter is suspended by a wire from a point of 80 centimeter from the load's left end. A. What mass must be hung from the right ends of the rod for it to be in equilibrium? B. What will be the tension in the wire? That is to say, now this is a uniform load. And I said from the first question, when you talk about the uniform, mean that have got the same dimension and the same mass at every point. Now, the diagram representation of the question is this one. Now, the length of the load is from here up to here, which have been said in the question is 130 centimeter. Now, from here up to here is 130 centimeter. But the wire is hung from, is suspended by the wire from the point 80 centimeter from the left end. Now this is left end and this is the right end of the load. Now this is the right end of the load and this is left end of the load, of the rods. Now if that had been the case, now from here up to 80 centimeter, it is where the wire was tied. Now the wire was tied to suspend these loads in 80 centimeter from the lefty, from the load's left ends. Now, this is the diagram representation. Kwa wa rod hii ni kutoka hapa mpaka hapa ambao ni 100 cm and 30 cm. Na imefunga waya kwenye urefu wa 80 cm kutoka kwenye rod's left end. Maana yake urefu wa kutoka huku kuja mpaka hapa ni 80 cm. Na kutoka hapa mpaka hapa ni 130 cm. Now, this is where the wire was hung from the Lord. Now, if that had been the case, we've been told to find out what the mass must be hung from the right end of the Lord for it to be in equilibrium, and what will be the tension in the wire. Now, note, at the point where the wire is attached is taken as the axis of rotation. This is to enable the tension of the wire to produce the moment. We have seen here, this is where the wire starts. Now this is taken to be axis of rotation. Why is it taken to be axis of rotation? To make this one be unable to produce moment of the force. This cannot produce the moment of the force because we have chosen this one to be the axis of rotation. And that is why it cannot produce the moment of the force. If we would have not chosen this one to be axis of rotation, this would have been, the moment of the force would be produced by the wire also. Now we have taken this one in order to say that this cannot produce the moment of the force because it has been chosen as the axis of rotation. And now the other thing, the two forces, those produces moment are the forces that will produce moments. After we have taken the wire at the axis of the rotation and in order to enable it to produce the wire, to produce the moment of the force. Now, the weight of the rod is the first force that will produce moment. The weight of the rod. The weight of the rod, as we have said earlier, the center of the mass is at its center. Now, the weight of the rod that is concentrated at its center of mass. That is midpoint. This is W. Now, this is the weight of the rod. Now, if this is the weight of the rod, it is always concentrated at its center. Uzito wa kitu uko katikati. Na sasa hatujaweka kitu katikati. Uninginiza katikati kwa maana kumbe uzito wa kitu utatengeneza moment of the force. And the second thing, that is the weight hung from the right end. The weight hung from the right end will produce the moment of the force. Kwa hiyo uzito utakaoninginizwa kutoka mwisho kwenye pembe ya mwisho kulia. Sawa? Kwenye pembe ya mwisho kulia na wenyewe utasababisha moment of the force. And now we want to know the distance from the axis of rotation to where 120 gram, which is the mass of the rod, and to where y, this is mass of the, weight of weight hung from the right end, that is the y. Now this is the w, this is the smaller than this one. Now, how do we know the distance? This is how we know the distance. The distance from here up to here is 80 centimeters. Therefore, the distance from here up to here, we take 130 minus 80 centimeters, which definitely we get is equal to 50. Now, from here, which is the y of it is where the y of the y starts, we say it is the distance from the distance from axis of rotation to where the mass is hung to the right end of the rods. Kwa hiyo kumbe kutoka hapa mpaka hapa ni 50 cm. But remember, this is not the center of the rod. The center of the rod is at 65. Now, from here up to here is 80. And from from here up to the center is 65. Now 65 is here, from here up to here, from here up to here is 80, and from here up to here, up to the center of the rod is 65. Now from here up to here is what? Now this is what now we have get, it is 15. Now 15 is obtained by taking from here up to here, which is equal to 80, and then from here up to here, which is equal now to what? To 65. Now 80 minus 65, you obtain the distance from axis of rotation to where the mass of the rod is says to be concentrated. and here up to here is 50 centimeter. Now you convert this one into, we have to convert this 120 gram into Newton. And we have to convert this 15 centimeter into meter. Why do we do so? We do so because this should be converted into force and this converted into meter to obtain the SI unit of, to obey the SI unit of moment, which is Newton meter. And that's why moments and clockwise moments, the mass of 120 gram should be converted to Newton, which is equal to 1.2 Newton. Is 15 centimeter from the axis of rotation. That is to say, it is 1.2 Newton times 0.15. Kwa tunachukua hii hapa tunaibadilisha kwa kilogram, kisha tunazidisha kwa 10 kwa sababu tunajua F is equal to mg. Mass is equal to 120, which is converted to kilogram, and then g is equal to 10. And that's why we say 1.2 Newton times 0.15 meter. Now we obtain 1.80 Newton meter. Now the total anti-clockwise moment is equal to 1.80 Newton meter. Now I have taken this one. I have taken 120 gram multiplied by 115 centimeter. But I've converted this one to meter and this one to Newton. Then this time this one is equal to this time this one. That is why I've said the total anti-clockwise moment is equal to 1.8 Newton. Then clockwise moment, the unknown mass hung from the right end is 50 centimeter, that is 0.5 meter from the axis of rotation. So the unknown mass, that is the mass is unknown. There is no given value for the mass. Now y is unknown mass times 0.5, which is equal to 0.5 Newton, 0.5 y Newton meter. So this is the total clockwise moment, which is equal to 0.5 y. Now we have obtained this 1.8 anti-clockwise moment and 0.5 y, this is clockwise moment. But from the principle of moment, anti-clockwise moment should be equal to the clockwise moment. Now anti-clockwise moment is equal to 1.8 and clockwise moment is equal to 0.5 y. Now when we divide by 0.5 both sides, you get y is equal to 0.36 Newton. Now this is Newton now. We need to convert this one. We need to convert this one Newton into mass. Because what we've been told is to find out the mass of an object and not the weight or the force of an object. Now, force is equal, we know force is equal to mass times g. Now we just want to obtain mass. Mass now is not there. Force is there. Now force is equal to what one? Now we take this force, then we multiply it by 10, we divide it by 10 to obtain 0.036 kilogram, which is g is equal to 10. Now we got this one. We convert this one into gram, we multiply by 1,000, which is equal to 36 gram. So the mass required is 36. Now we have get this one. You convert this Newton by using principle of F is equal to mg. Now means mass is equal to force times, force over g. Now force over g is equal to 36 gram. Now the mass required is 36 gram. For the load to be for the load to be in translational equilibrium, the tension in the wire must be equal to the total weight of the rod and the hanging mass. Now in order for the tension to be able to handle the rod, the tension in the wire must be equal to the total weight of the rod and the hanging. Now the total rod, now the total mass. Now the tension on the wire should be equal to the total mass, or the total mass of the rod and the mass of the mass that will be hung at the right end of the rod. So we have got here 36 gram and here we have got 120 gram. So when you add up them and then you convert them into tension, then 36 you get 156 gram. Then you convert them into kilogram. After you have converted them into kilogram, you convert them into Newton. That is the tension. That is why we have said the tension is 1.2 Newton. That is for the 120 gram and 0.36. That is for 36 gram, which is equal to 160 1.56 Newton. Now the tension of the wire is equal to 1.56 Newton. Now let us see on the blackboard how we can solve this. We have seen on the projector. Now let us see more different on the blackboard. Now we say, the question said that a uniform rod with a mass of 120 grams and a length of 110 centimeter, 130 centimeter, is suspended by the wire from the point of 80 centimeter from the load's left end. Now the length of this one is from here up to here, 130 centimeter, just from here. This is the length. Now, if this is the length, we've been told this load is suspended by the wire from point of 80 centimeter from the left ends. The left end is here, so this is left and this is right. Now, when you say from here up to somewhere like here, this is 80 centimeter. It is 8 centimeter. It is 80 centimeter. Now, it is 80 centimeter from the load's left ends. Now, the question is, what is the mass must be hung from the right end of the load? The mass that will be hung from the right end of the load. Now, let's say this is 1. But this mass will be balancing. This mass will be balancing with the mass of an object. Example, this is the mass of an object. If this is the rod, now this is what the rod I'm talking about. The rod I'm talking is that this is the center. Now if I hang it here, if it is this center, it will go this way. Now I balance with another force here. So I've applied here force, but I am balancing with the force of the rod. I am balancing with the force of the Lord. And that's why this is balancing with the force of the Lord. Now, the force of the Lord is given from the mass of the Lord, which is stated that it is center. Now, let's say it here, it is 120 grams. Now, this is to say the distance from here up to here is 80 centimeters. But from here up to here, it is 130. Now here it is 50 centimeters. And also, the distance from here up to here is 80. And the distance from here up to here is 65 centimeters. Because this was that it is midpoint. Now, if here up to here is 65 centimeters, then from here up to here is 80. Now, 80 minus 65, which is equal to 15 centimeters. Now, that is what? Now, we just want to know the distance from the axis of rotation is equal to 15 centimeters to the mass of 120. Therefore, 120 is converted to Newton, which is equal to 1.2 Newton. Then, this is multiplied by this one. Now, you get, that is, we say this is an anti-clockwise moment. Now, anti-clockwise moment is equal to 1.2 times the distance from the axis of rotation is 15. Now you divide by 100 times 0.15. Now it should be equal to the clockwise moment. Now the clockwise moment is equal to this force. Now let's say force is equal to y times. Now the distance, this is the distance from the axis of rotation to point where the mass is placed. Now which is equal to 0.5. Now, when you obtain this one, you definitely get it is this and this one. Then you divide by 0.5, and then here you divide by 0.5. Now, y is equal, then you got is equal to 0.36. This is Newton. So this 0.36, it is Newton. But we have not asked the Newton. So what you do is you convert this one into program. From F is equal to mg, then mass is equal to F over G. Now remember force we have got, it is 0.36, you divide it by 10, which mass now is equal to 0.036 kilogram. So this is the kilogram. Now you convert this kilogram into gram, that is multiplied by 1000. Then you get mass is equal to 0. Now when you multiply by 1000, you got 36 grams. So the mass that will be hung at the right hand of the Lord is 36 grams. But also we've been told to find the tension of the wire. The tension of the wire is obtained by taking this mass, this weight, and this weight. Remember here Newton is 1.5, 1.2. And here Newton, we have got 0.36. Now, hizi zote ili ziweze kushikiliwa na wire, lazima hii kujumlisha hii sawa sawa na hii. Then tension is equal to 1.2 times 0.36, then which is equal to 1.56 Newton. So this is the tension of the wire. Otherwise, kama hizi huku zitazidi tension of the wire, tension wire itakatika. Na ikikatika wire, maana yake there is no enough tension to hold these two masses. Therefore, we say the upward force should be equal to the downward force. For the tension to be in equilibrium, for the tension to be able to hold on these things, that should be equal in magnitude. And that is what we do. Hapa tunaangalia forces in equilibrium. Sawa? Ni kama marudio. Mimi nimeandika maswali hapa mawili yakawatosheni. Ndio. Yasipowatosha maswali mawili nitaongeza mengine mawili. Ambao ile weight of the ruler lipo pale. Sawa? Lela mwanamke mjibu wake ni pale. Kwa mifano miwili hii ni forces in equilibrium. Kwa mimi nimeleta haya nimwambia kidogo. Haya ni kama matakataka. Kama ungekutana nayo haya unaweza ukasema huyu naye vipi? Ameanza kuchizi au kumbe ni kawaida. Hivi ni vifaa vya kufundishia tu leo. Kwanza tushajifunza vizuri principle of moment. Tunajua si ndio? A principle of moment for the system to be in rotational balance, and clockwise moment should be equal to the clockwise moment. Manake the sum of anti-clockwise moment should be equal to the sum of clockwise moment. Sawa? Kwa hapa kwa sababu tunajua what is the principle of moment. A principle of moment states that for the system to be in rotational balance, the sum of clockwise moments should be equal to the sum of anti-clockwise moments. Hiyo ni principle. Tumeziona. Manake za upande huu lazima ziwe na za upande huu. Ni sawa na hiyo. Sawa? Mimi nafanya anza tu hapa. Najua baadaye mimi ni maandamia baadaye. Unaona hapa? Manake za huku na za huku zimebalance. Naweza mimi nikampimia mtu, nikampimia kwa kutumia tu yale mawe ya kilo, ya mzani yale, nikampimia mtu. Bila hata kutumia ule mzani. Lakini nani ataniamini mpaka aliyesoma? Lakini tunatumia kwa sababu ile mzani uliotengenezwa pale hauna chochote zaidi ya kuhakikisha kwamba huku ina balance na huku ina balance. Kwa maana hiyo mimi naweza nikasema bana unataka kilo ngapi? Nikapima tu distance. Kwamba distance ya kutoka hapa na distance ya kutoka hapa nataka zifanane. Lakini wewe variation ni mass. Kwa nikaanza kubalance. Zikilingana tayari mimi nakwambia kilo zako 5 hizi hapa. Lakini nani ataniamini? Kija dukani kwangu nikwambia bana mimi sina mzani. Lakini mawe ya mzani ninayo. Haya hapa. Ila mzani sina. Kwa na kupimia kwa kutumia mti wangu hapa. Nikimaliza kupima utaniambia wewe mshenzi umechizi. Hebu rudishie hapo ile itanue dukani sehemu nyingine. That's a principle kwa sababu we have no knowledge of forces in equilibrium. Kwa sababu huyu amebalance huku na huku. Kwa sababu za huku na za huku zinafanyaje? Zinafanana. Hiyo ndio tunaita forces, tunaita principle of moment. For the principle of moment, for the system to be in rotational balance, ili system in balance, manake the sum of clockwise moment should equal to the sum of anti-clockwise moment. Na ndio maana mmeona nimebalance. Nothing I've done. Lakini uzito huku na huku umebalance. Hiyo ni principle of moment. Sasa mimi nimejaribu kusema maswali hapa mawili. Ukiangalia hapo swali ni jepesi, lakini linahitaji kuwa na knowledge. A uniform metal loop is pivoted at its center. A uniform metal loop is pivoted at its center. Tunaposema something uniform, kitu ambacho ni uniform manake ni kama hiki. Hiki ni mfano wa uniform. Pengine labda sijaeleweka, hii nao ni mfano wa nini? Wa uniform. Uniform manake ni kwamba there is no variation in heads. Simeelewa vizuri? Hakuna sehemu ambapo ni nyembamba, hakuna sehemu ambapo ni nene, manake ni kwamba urefu, yani hapa pote panafanana. Sehemu zote zinafanyaje? Zinafanana, sio kwa sura, kwa vipimo. Ukiangalia distance, ukiangalia hapa upana kutoka hapa mpaka hapa ni sawa na upana kutoka hapa mpaka hapa. Maana pote hapa ni sawa na huku pote ni sawa. Hiyo ndio tunaita uniform. Ikiwa huku ni nene, huku ni nyembamba, hapa katikati na shimo, that is not uniform. Kwa tunaposema a uniform metal loop, maana ni metal ambayo vipimo vyake, maana hii huku ni sawa, hapa ni sawa, hapa ni sawa, hapa ni sawa, hapa ni sawa. Vipimo pamoja na unene wake. Ndio tunaita a uniform metal loop. Kwa when we say about a uniform metal loop, tunamaanisha tu kwa mfano tumeambiwa uniform, maana yake tunaichora hivi. Tumeelewana vizuri? Mimi nimechora hivi. Lakini kama ni metal loop, maana yake it is 0 up to 100. It is a uniform metal loop. Manake ni sentimita 0 mpaka 100 ni mita 1. Kwa maana hiyo from here up to here 100 cm. Sasa tunapoambiwa pivoted at its center, the point of pivot, manake ile fulcrum, ile egemeo ipo katikati, center katikati. The midpoint between 0 up to 100 is 50. Kwa maana yake ni nini? Huku ni 50 cm na huku ni 50 cm. Hiyo ndo language ya kwanza. Maana yake every statement have got its meaning. Kila sentensi ina maana yake katika forces in equilibrium. Kwa sentensi ya kwanza mimi nimedefine hapa kwamba a uniform metal loop and it is pivoted at its center. Point ya pili anakuambia a 20 gram mass is placed at 10 cm mass. 10 cm mass. Manake imewekwa kwenye sentimita 10. Kwenye point ya sentimita 10, sio sentimita 10 kutoka kwenye fulcrum. Manake siku nyingine utaambiwa 20 gram was pressed 10 cm from the fulcrum. Ni sentensi nyingine. Manake huo ni umbali wa kutoka kwenye fulcrum to where the mass is placed. Kwa hiyo tumeambiwa hivi 10 cm mark. Kwenye alama ya sentimita 10. Kwenye alama ya sentimita 10 ndo pale uzito umefanyaje? Umewekwa. Lakini nakwambia 10 cm from the fulcrum, manake ni umbali sasa wa kutoka hapa mpaka pale mzigo ulipowekwa. Lakini kwa sababu nakwambia 10 cm mark, ingelikuwa metalu hii ina lebo, manake sentimita 10 zingekuwa ziko hapa. Kwa pale ndo mzigo ambao umewekwa, ambayo ni 20 gram. Kwa manake from 0 to 10 cm. For 10 cm it is from 0 to where the mass is pressed, and that's why we say 10 cm mark. Kwenye alama ya sentimita 10 ndo mzigo wa gramu 20 umening'inizwa. Sasa kwenye sentimita 10 haiwezi ikawa huku mpaka hapa ni 50. Ambacho nakisema kuna maneno mazuri ambayo ni ya msingi. Umeambiwa 10 cm mark kwenye alama ya sentimita 10. Lakini kama angelikuwa amekwambia 10 cm from the axis of rotation. 10 cm from the axis of rotation. Au 10 cm from the fulcrum. Manake ule umbali unakuwa kutoka kwenye pivot kwenda pale mzigo ulipo. Na haiwezi kukwambia hivyo. Kwa sababu akikwambia hivyo swali litakuwa difficult mno. Kwa sababu hauta calculate distance, uta substitute to the case will be over. Lakini sasa baada ya hapa akasema a 50 gram mass at the 40 cm mark. Kwenye sentimita 40 akaning'iniza mzigo mwingine wa gramu 50. Bado mpaka hapa ni 50. Kwa bado 40 iko huku. Kwa manake kwenye 40 imagine umeweka hapa sentimita gramu 50. Gramu 50 manake from here. This is 40 cm. Bado hatujaigusa hii. Kwa kwenye alama ya sentimita 40 alining'iniza mzigo wa gramu 50. Halafu anaulizaje? At what mark must a second 50 gram mass be placed for the system to be an operational balance? Kwa hiyo unaulizwa ataweka katika sentimita ngapi mzigo mwingine wa pili? A second 50 gram mass must be placed for a system to be an operational balance. Ili balance ataweka uzito sehemu gani? Kwa maana hiyo haiwezi ka balance ile 50 nyingine kama tutaiweka huku tena. Inabidi tuiweke upande wa ngapi? Wa pili. Lakini hatujui ni alama ipi au kwenye sentimita ngapi. Kwa tuna imagine kwamba sisi tumening'iniza hapa gramu ngapi? 50 za pili. Gram the seconds. A second 50 gram tumening'iniza hapa. Kwa maana hiyo kwa nini nimeweka upande wa pili? Is balance. Lazima niweke upande wa pili. Sasa tufanye tu experiment, a simple experiment. This is mimi hii hapa nimetalu. Tuangalie katikati. Kwanza kujua katikati pamoja na hii kwamba haina vipimo ni kupima tu kwa kutumia hii. Kwa sababu we have center of mass. Center of mass for a uniform body is concentrated at its midpoints. Tunaposema center of mass is a point where the mass of the body says to be concentrated. Ni point ambapo uzito wa kitu umekuwa concentrated. Kwa nikining'iniza hii hapa ikibalance horizontally, manake uzito wa kile kitu uko pale katikati. Sasa nitawajibu kwa nini lula hapa haita produce moment. Itakapo balance ndo katikati ya hiki. You have to be very careful. Mwone balance. Sasa kwa sababu tumeweka midpoints katikati. Kwa sababu kuna principle here. Moment is equal to force times what? Distance. For force is there kwa sababu inakuwa produced by the mass of an object. Lakini the distance we deal with, ndo hapo naenda kujibu kwamba hapa lula haita produce weight, haitakuwa na moments. Kwa sababu gani? The distance that we deal with is the distance from the axis of rotation. It's the distance from the pivot. It is the distance from the fulcrum. That is the distance that we deal with it. Umbali ambao tunashughulika nao ni umbali ambapo kutoka kwenye axis of rotation mpaka pale mzigo ulipo. Sasa kwa principle ya center of mass, uzito wa rula upo katikati na ndipo ilipo axis of rotation. Maana yake distance itakuwa sawa sana ngapi? Na 0. Kwa rula haita produce moment kwa sababu a distance is 0 from the axis of rotation. Lakini ikiwa imeweka pembeni ndio swali linalofuata. Tajibu. Kwa hiyo hapa the ruler will not produce the moment because the distance is 0 from the axis of rotation. Kwa nini nasema hivyo? Uzito wa hiki kitu uko katikati. Na ndipo pale ambapo ameweka axis of rotation. Ndipo pale ambapo ameweka pivot. Kwa hiyo huyu hata produce moment hata kama angekuwa mzito namna gani. Lakini kitokea sasa siku nyingine hajaweka katikati na lula inakuwa considered. Kwa itatokea sasa, itatokea hivi. Kwa mfano, hii itatolewa pembeni kidogo au itasogezwa pembeni kidogo. Huku upande huu kutakuwepo na mass of the ruler na kutakuwepo na mass hii hapa. Haikuchezea hivyo. Don't bother. Just understand the concept, what matters. Kwa kinachofuatia sasa hapa ni kama kifuatacho. Mimi nimewambia hii hapa na mizigo hii hapa miwili. Moja ni gramu 20 hii hapa. Nimeweka kwenye sentimita ngapi? Sentimita. Moja ile support. Moja tu ile support. Ashikilia. Sasa akiachia huyu bwana mkubwa inadondoka huko. Simelana. Usiomba achie. Kwa sababu wengine ni mchaka kichwani. Wanafikiri kupoteza muda ni kuendelea hivi. Sawa? Kwa hiyo nimeweka gramu 20 hapa. Sentimita, 10 cm. Sina vipimo. Halafu nikaambiwa tena nyingine 50 gramu kwenye 40 cm. Naweka hii. Mimi sijui kama ni 50 but just an experiment, a simple experiment. Naweka hapa. So this is 20 gram I've approximated and this is 50 gram. Sasa ya pili hili niweke. Lazima niweke upande wa pili. Ni kubwa sana sijui. Hata hivi. The other 50 gram siwezi nikaiweka huku. Lazima niweke wapi? Huku. Ili si balance. Kwa ni naulizwa, hili ndio swali linauliza. Je, nitaiweka umbali gani ili balance? Sasa ndio naanza kujaribu. Unasogeza mpaka itakapo balance. Tunaendelea. Hii sio miujiza. Sije ukasema miujiza. This is not a miracle. I did it. Thank you, Jesus. That is the balance. Yes. Sawa? Sawa? Maana nilipofanya hii ndio swali. Maana yake ni kwamba sasa msikilize. Pengine haiwezekana mimi nilikuwa nasema hapa, nafanya hapa, I've spent a lot of time kuhakikisha kwamba ina balance. Lakini sasa ni balance, elewa umuhimu wake sasa. Umbali ambao tunashughulika nao, the only distance that we deal is kutoka kwenye fulcrum kwenda kwenye mzigo. Kutoka kwenye fulcrum kwenda kwenye nini? Kwenye mzigo. Kwa hiyo this is 20 gram, this is 50 gram and this is the other 50 gram. Sasa ningeiweka upande wa huku isinge balance. Lakini nimeweka upande wa huku ili kubalance. Na ndiyo swali sasa kwa nini nimeweka upande huu. For the system to be rotation balance, I must press the second 50 gram to the right of the ruler. Hali na balance. Sasa from here up to here, we don't know the distance. Kutoka hapa mpaka hapa hatujui umbali wake. Kwa nini tunashughulika na umbali kutoka hapa mpaka hapa? Nimwambia the only distance we deal with is the distance from the pivot to where the mass is pressed is the distance from the axis of rotation to where the mass is pressed. Umbali ambao tunashughulika nao sio umbali wa kutoka hapa kuja hapa. Wala umbali wa kutoka hapa kuja hapa. Au umbali wa kutoka hapa kuja hapa. Ni umbali wa kutoka kwenye axis of rotation mpaka pale mzigo ulipo. From here up to here is 1 centimeter. From here up to here is 1 centimeter. Now the distance from axis of rotation to where 50 mass is pressed is what? The pile calculation is naanza. Kama kutoka hapa mpaka hapa ni 40. Na kutoka hapa mpaka hapa kwenye axis of rotation ni 50 centimeter. What about here to here. 10 centimeter. Now the distance here it is 10 centimeter. Kama kutoka hapa mpaka hapa ni sentimita 10. Na kutoka hapa mpaka katikati ni sentimita 50. Je, kutoka hapa mpaka pale mzigo ulipo ni sentimita ngapi? 40 centimeter. Kwa umbali ambao nautafuta mimi ni umbali wa kutoka kwenye axis of rotation kwenda pale mzigo ulipo. Sio hivi 10 cm na 40 cm ambazo zilikuwepo pale. Zinakurahisishia tu kupata the distance from the axis of rotation to where the mass is located. The distance from the axis of rotation to where the mass is located. The distance from the axis of rotation to where the second 50 gram is located. Ndio hiki ambacho nakisema hapa. Kwa inawezekana mimi nikaweka huyu huku na huyu huku mbali mbali, mwingine akawa mzito, mwingine sio mzito, lakini wanaweza wakabalance. Kinachofanyika ni nini? Yule ambaye ni mzito, distance inapungua from the axis of rotation, halafu yule ambaye ni mwembamba kama mimi, distance inaongezeka ili kubalance. Kwa from there, tayari sasa kutoka hapo we have this one. Swali ni kuchora. Yaani haya maswali ni kuchora tu. Ndio shida. To calculate no problem. Now the 50 gram, here 50 gram is from 1 centimeter. The other 50 gram is 10 centimeter from the axis of rotation. But the other 20 gram, this is 50 gram. The other 20 gram, it is 40 centimeters. Now, hapa kuna alternative hizi. Ukishafika hapa, kuna alternative hizi. Moja ni shortcut. Sawa mani? Ndio. Ya pili ndio unaotakiwa kuifanya. Lakini kama jua liko machweo, lazima uelewe kwamba principle ni ipi. Njia ya kwanza ni kwamba unaangalia za unclockwise, hizi ni clockwise moment. Clockwise moment. Sasa hapa manake you have 20 gram times the distance of this 20 gram from the 5 gram. Ni ngapi jamani? 40 plus za huku zote 50 gram times the distance from the axis of rotation is what? 10 cm. Is equal. Manake unclockwise moments is equal to clockwise moments. Now it is 50 gram times y. We are looking for the value of y. Over 50 here. Over 50. Now, this and this one, 800. Plus, this and this one, 500. Over 50 is equal to y. Now, here plus this one, this one. Over 50 is equal to what? Y. Now cancel. Now the value of y is what? 1, here it is 20 what? 26 centimeters. Now from here up to here is 26 what? Now this is the distance from the axis of rotation. It is not the answer that you've been told. Here umeuliza nini? At what mark? Kwenye sentimita ngapi atanimiliza mzigo? Haujaulizwa what is the distance of the axis of rotation from the axis of rotation where the mass, the second 50 gram is placed. Haujaulizwa hivi. Umeulizwa katika sentimita ngapi ataniuza mzigo. Remember, up to here is 50 cm. Ukiongeza 26 na kwa ngapi? 76. Kwa hiyo 76 mark. 76 cm mark. Kwa hiyo mpendwa, nikwambie kitu kimoja. Kama there is gram and centimeter, don't bother. Usijisumbue sana. Maanake gram times centimeters is possible. Kwa umbali ambao tunashughulika nao ni umbali kutoka kwenye axis of rotation mpaka pale mzigo ulipo. Umbali kutoka kwenye axis of rotation mpaka pale mzigo ulipo. Ni umbali ambao. Baada ya hapo hii mara hii kujumlisha hii mara hii sawa na hii mara hii. Maana yake clockwise moment is equal to clockwise moment. Maana yake jumla ya hizi huku sawa na jumla ya hizi huku. Hata kama zingekuwa na mfano huu hapa. Huku hapo wawili, huku yuko mmoja. So balance. Ndio. Njia nyingine sasa ni hii hapa. Unaanza na anti-clockwise moments. Anti-clockwise moments. Now, unaanza for 50 gram. For 50 what? Gram. For 50 gram. Sasa, for 50 gram. Moment is equal to force times what? Distance. Lakini distance must be written in terms of meter. 50 gram is 10 centimeter. Now distance is equal to 10 centimeter. Convert it into meter. Remember 1 meter is equal to 100 centimeter. Kwa maana hiyo sasa hapa we get 0.0 divide by 100 get 0.1. Sasa remember force is measured in terms of Newton. Kwa maana hiyo 50 gram unaiconvert kwenda kwenye Newton. How? F is equal to mg. Mass times gravitation constant. But this mass must be converted in terms of kilogram. Lazima ile hapa mass sasa unabadilisha kwenda kwenye nini? Kwenye kilogram. Ambao unapata 0. ngapi? 1000. 0.05 kilogram. Now you have mass which is 0.05 times G which is constant 10 Newton. Now if you multiply you get 0.5 Newton. For force, now force is equal to 0.5 Newton. Now you can multiply. For moments, itakuwa sawa sana force times what? Distance. Which now force, it is 0.5 Newton times distance. Distance is 0.1. Ambapo moments for 50 gram itakuwa ni 0.05 Newton meter. For 50 gram, moment is 0.05 Newton meter. Now, if that is the case, for 20 gram, ambayo hii hapa is equal to 0.02 kilogram. Kwa maana yake distance yake hii it is 40. Distance is equal to 40 centimeter which is equal to 0.4 meter. Kwa tukalculate force hapa, since force is equal to mg, now force is equal to 0.02 times 10 which now is equal to 0.2 Newton. Sasa tayari mmepata force. Remember moment of the force. Let us do it in where? Here. Moment of the force is equal to force times what? Distance. Force is 0.2 times distance 0.4. Now moment is equal to 0.08. This is 0.08 Newton meter. maana yake ni kwamba tayari for 20 gram and for 50 gram tayari tumezipata hizo moment. Lakini kumbuka zote ziko kwenye anti-clockwise moments. Now, the total anti-clockwise moment. Total anti-clockwise moment is equal to 0.08 plus 0.05, which now is equal to what? 0.13 Newton meter. Kwa hizi zote ni za anti-clockwise moment. For 50 gram, we have got 0.05 Newton meter. For 20 gram, we have got 0.08 Newton meter. Now, the sum of anti-clockwise moment is equal to, for 50 and for 20, Juma tutapata 0.13 Newton meter. Now, what next? Clockwise moments. Now, clockwise what? Moments. Tunayo moja tu. For 50 what? 50 gram. Which now is approximated to 0.05 kilogram. Now, F is equal to mg. Now, 0.05 times 10. Now, which is equal to what? 0.5 Newton. But the distance for the second mass is y. Now, it is, distance is what? Y. Kwa tunajua kwamba anti-clockwise, kwa hiyo tayari hapa moment is equal to force times what? Distance. Force is 0.5 Newton times distance, which is what? Y. Now, from the principle of moment, this is already the moment and clockwise moment. Kwa sababu ni clockwise moment, kwa sababu hatuna nyingine. Now, from the principle of moment, the anti-clockwise moment is equal to the clockwise moment. The sum of anti-clockwise moment is equal to the sum of clockwise moment. Anti-clockwise moment, we have done it is 0.13, which now is equal to clockwise moment 0.5y. Now we are looking for the value of y. We are looking for the value of y. Now y is equal to 0.13 over 0.5, which now is equal to 13 over 50. Now which is equal to 0.226. Now y is equal to 0.26 meter. Kwa sababu relation was meter. Now convert this 0.26 into centimeter. You get what? Times 100. Now y is equal to 26 what? Centimeter. Now tumesema yeye kwamba kama hapa ni 50 ukiongeza 26 inakuwa 76.76 centimeter. Tumeelewana jamani? Are we together? Yes. That's all. Nena swali la pili. Nena swali la ngapi? A uniform log with a mass of 120 gram and a length of 130 centimeter is suspended by a wire from a point 30 centimeter from the load's left end. Hii sio rula, ni kitu cha kawaida. Kama hii. Hii sio rula. Sasa kwa sababu tunaambiwa imening'inizwa, likiwa katikati, tunaweza tukatafuta tu katikati. Mimi sijui kama naweza nikatafuta, lakini possibly tunaweza tukafanya. Kwa katikati ni hapa. Sawa? Imebalance sasa tuseme labda, si ndio? Sasa kama hapa katikati nikisogeza huku itadondokea kule katikati. Nikisogeza huku itadondokea kule katikati. Kwa hiyo naweza nikaweka mzigo mimi huku nikabalance hili jamaa bila hata shida. Sijaweka kitu kule. Mebalance. Sijaweka nini? Sijaweka kitu kule. Maana yake nini kimebalance? Uzito wa hii rula. Kwa sababu huko kule una balance na hii. Si tumelala jamani? Maana yake ni nini? Ndio hilo swali. Ikiachia tunadondokea kule. Sasa ndio hii hapa swali. Unaambiwa urefu wa kitu hiki refu namna hii. Refu namna hii. Refu namna hii. Na huku refu namna hii. Refu namna hii. Refu namna hii. Tumeambiwa urefu wake ni sentimita 100 na ngapi? Maana yake from 0 to 130 centimeter. Is suspended by a wire from a point 8 centimeter from the left ends. Mbona haya maneno yameanza kusema sasa? Kutoka mkono wa kushoto imening'inizwa ubao, umening'inizwa au hiki kitu kimening'inizwa kwenye sentimita ngapi? 80. Kwa sentimita 80, imagine ni hapa ndo amening'iniza waya. Maana yake from left to where the wire is tight is 8 cm. Sasa utajua hii 8 cm inakusaidiaje. Anakuambia hivi. Halafu akakuuliza hivi, what mass must be hung from the right end of the Lord for it to be in equilibrium? Anakuuliza ataning'iniza mwishoni kabisa hapa uzito kiasi gani? Mimi sijui, anasema yeye uzito ambao haujui ili iweze kubalance. Sasa ina balance na nani? Ina balance na uzito wa rula. Kumbuka uzito wa kile kitu rod, uzito wa kile kitu ni kwamba kama hii hapa, nimewambia narudia tena hapa kwamba nitakapoweka uzito wangu huku si balance na mzigo wote, isipokuwa uzito wa hiki kitu ndio na balance na uzito huu hapa. Lakini uzito wa hiki kitu uko katikati. Kwa katikati ya 130, the midpoint of this 130 is 65. Maana yake katikati sasa ya huyu ni 65. Kwa kutoka hapa mpaka hapa 65, katikati ndio utaning'inia ule uzito wa yule wa hiki kitu wa hii load. Kama ni ubao. Kwa hapa ndio utaning'inia ule uzito wake ambao ni 100. Ni ngapi tumeambiwa? The mass is what? 120. Hapa ndio uzito utakaponing'inia ambao ni 120 grams. Kwa hiyo uzito wa hiki kitu kutakuwa na maana yake from here up to here 65 cm. And from here up to here also is 65 cm. Lakini umeambiwa from here up to where the wire is tight is it 8 cm. Haya swali limeisha. Kwa sababu tayari hapa ni 120. Tunataka kwa hiyo hii hapa ambayo imening'iniza hapa ndio ina act kama axis of rotation. Kwa mimi nikishika hii hapa ndo katikati. Nikishika vizuri katikati ita balance. Tayari imebalance. Sawa? Lakini nikisogeza mkono wangu huku hivi, nimening'iniza na ashumu mkono wangu ndo waya. Naondokea huku. Kwa kule ndo uzito, pale katikati ndo uzito wa kitu. Nikishika tena huku itadondokea huku. Kwa sasa ina balance. Ili sasa mimi nimeshika hapa sasa hivi. Nimedondokea, naweka uzito hapa. Nimekandamiza hapa balance. Ndo anauliza uzito ni kiasi gani ili si balance. Kwa from the question is very simple now you can see. Look at here. Sorry. From here up to here is 65. From here up up to the next end is 65 volts. Lakini, I've told you, the only distance that we deal with it is the distance from the axis of rotation. So, the distance from the axis of rotation to where the mass is placed is from here up to here. And it is from here up to here. Kwa hizi tulizokuwa 65-80 hizi zinatusaidia kupata sasa umbali wa kutoka hapa. Kwa this is the axis of rotation. Kama kutoka hapa mpaka hapa ni 80. Na kutoka hapa ukakomea hapa ni 65. Ili nikamilisha 80. Imebaki ngapi? Now, the distance from one point to where, to the axis of rotation is 15. Kwa hapa ni 15 cm. Kutoka hapa mpaka hapa. Now, there also the distance from the axis of rotation to where the mass y, which is a known mass. Lazima tujue. From here up to here is 80. See the one? Lakini the whole length from point O to here is 1/3. Kama kutoka hapa mpaka hapa ni 80. Ili kukamilisha sasa hiyo 130. Zimebaki ngapi kutoka hapa mpaka hapa? Now 50 cm. From here up to here. Manake, kwani tumezitafuta hizi? Hizi ndizo tunazoshughulika nazo. Kwa hiyo huku sisi hatuna shida nayo. Hatuna shida na 65, 130, 380. We don't mind them. What matters is the distance from the axis of rotation to where the mass is pressed. Now, what next? Very simple now. We can calculate. Sasa si hii mara hii. Sasa na hii mara hii. Now it is very simple. 120 gram times 15 centimeter is equal to 50 centimeter times y. Now divide by 50 centimeter. Now you divide here by 50 centimeter. Now centimeter went out. Now this and this. Then by here. Then it is 12 times 15 over 5. 1, here it is what? 3. Now it's equal to what? That what? 36 grams. Now the mass that is suspended here in order for the load to balance is what? 36. So what is that? 36 grams. How is it? The only problem is interpretation of the question. Changamoto ni kutafsiri ile swali na kuliweka kwenye mchoro. Hapo ndo patamu. Sio kucalculate. Calculation kwenye forces in equilibrium is not a problem. The only problem is to interpret, to make an interpretation for the question. Maana yake kufanya diagram representation of the question ndo shida. Lakini ukielewa hizo point ambazo nakwambia, kwanza lazima uelewe center of mass. Kwamba center of mass is the point where the mass of the body stays to be concentrated. Manake, for the uniform body, the center of mass stays to be concentrated at its midpoint. If now we talk about 60 centimeter, 30, that's where the point of mass stays to be concentrated. Hiyo ndo point ya msingi sana. Haya mengine hapa, yaani kuchora ndo shida. Kuchora ndo mziki. Sio calculate. Lakini ukielewa, the distance that we deal with, the distance from the axis of rotation, na ukiambiwa place at the 10 cm mark au the 10 cm from the axis of rotation, hizo ndo point tunataka kuzielewa. Kwa hiyo tumeuliza hivyo sasa. Tunaenda kipengele cha mwisho. What mass must be placed must be hung from the right end of the rod? We have got that is 36 grams. What will be the tension in the wire? Nikifanya hivi, usicheke. Mbona hivi? Simona, nimeweza hata kama naweza kubebwa kwa sababu lula ina uwezo wa kuhimili hiyo kitu. Kama inatokea naweka mzigo mzito, lula inakatika. Wewe umekaa kwenye benchi, kama unatokea kuliziti benchi, tayari linafanyaje? Linavunjika. Kwa kama mimi Maana yake ni kwamba tumekubaliana. Pengine tu nanili begi langu hili. Mtoe tu mfano. Naona a very simple. Here, you know somebody you have to be crazy when teaching physics. It is something fun. Naona ya. Sasa kamba hii ikizidiwa na huu mzigo inakatika. Lakini sasa imeweza kushikilia mzigo kwa sababu uwezo wa kushikilia, uwezo wake ambao ni tension yake ni sawa na weight ya begi hili. Kwa kama aliweza kuning'iniza hivi ile vitu, alining'iniza vitu vingapi jamani? Uzito wa ile lula au ule ubao na uzito mwingine aliouongeza pale, vyote viliweza kushikiliwa na ile waya. Maana yake ni kwamba kumbe tafsiri yake tension ya waya sawa sawa na weight ya vile vitu vilivyoning'inizwa. Ingetokea weight imezidi ile tension yake, kamba inakatika. Fana mzuri tu. Najua wakati mwingine Mungu tunamsingizia. Mtu anaenda kujining'iniza, anataka kujinyonga kwa kutumia kamba. Halafu ile kamba akaizidi tension ikakatika. Halafu akamwambia Mungu ameniokoa. Pumbavu. Ungepima tension, ungekuja tukathibitisha tension ya kamba, tukakwambia tension ya kamba na tension yako na uzito wako vinaendana. Nenda kajining'inize. Ikikatika basi Mungu atakuwa anakusaidia. Wakati mwingine tunamsingizia Mungu. Unaenda kumjaribu. Maana yake nini kwa tafsiri hii? Mimi sipimi imani. Nasema tu according to physics. Imani sasa tunaenda nayo sawa. Hata mimi naamini. Sasa maana yake tension waya ni hapa. Lakini waya umefungiwa mizigo miwili. Mzigo wa kwanza tunaona ni 36 gram. Mzigo mwingine tunaona ni 120 gram. Sasa hapa downward force. Downward. Halafu huyo anavuta juu, upward force. For the system to be in a equilibrium system. Condition for equilibrium. Tunazo ngapi? The sum of opposite forces must be equal. The second condition, the anti-clockwise moment should be equal to the clockwise moment. That is the principle of moment. What the condition is B. Kwa mimi nikishikilia hapa mawe yangu hivi, mimi nalazimisha mawe yasishuke chini. Na apply force, upward force. Lakini mawe yana apply downward force. Sasa kwa sababu nimeweza kushikilia hapa, ni kwa sababu tu upward force is equal to the downward force. Na ndio kinachotokea hapa. Kwa ndio kinachofanyika ni kwamba, kwa hiyo force hizi ni huyu na huyu. Kwa maana yake we have upward force itakuwa ni 120 gram plus sayani plus what? 30 gram. Sasa na tension of the 36. Kwa itakuwa ni 150 gram. Sasa na tension. Remember tension is measured in terms of Newton. Kwa badilisha tu hiyo kwa Newton. Sawa man? Ambao ukigawanya kwa 1000 inakuwa ni 0.156 kg times 10 Newton per kilogram. Kilogram anaondoka. Tension is equal to 150, then it is 1.56 Newton. Tension itakuwa 1.56 Newton. Ndio hivyo tu. Lakini the most important point was supposed to be applied here. Manake ni principle of moment. Tumemalizana nayo kwenye swali la kwanza. Ya pili ni ile condition for the equilibrium. In order for the body to be in equilibrium, two conditions must be satisfied. The first one, the sum of the opposite forces must be equal. Manake zile kama nyingine ni upward, nyingine down, lazima zifanane. Ndio kitu kita balance. Condition ya pili ni kwamba for the system to be in equilibrium, the sum of anti-clockwise moment must be equal to the sum of clockwise moments. Tayari. Tumelana jamani? Tumelana? Kila mwana amenielewa vizuri? There is no problem. Hiyo ndo forces in equilibrium. Kama umenielewa, kafungue kitabu chako, anza kufanya. Basi hautakosa hata swali moja. Hiyo ndio inaitwa forces in equilibrium. Now we are done.